I'd like to thank the organizers for the opportunity to speak here in substitution for Mike, who sends his regrets. So this is joint work with Evan Golick, James Hall, and Joris Frankenschäfer, who are all at UCSD at some point in time. And Evan's currently an assistant professor at the University of Hawaii. And it's very generously funded by the National Science Foundation and more recently by the Air Force. OK, so let me try to frame it's like what we're interested in doing. I mean, part of the reason, of course, we're all here is because of the interest in gravitational waves. And of course, gravitational waves are ripples in fabric of spacetime, which were predicted by Einstein back in 1916. And they were first directly observed, it's like in 2015 by the Advanced LIGO project. And there's a sense in which one isn't simply interested in detecting gravitational waves, but essentially doing the inverse problem of trying to figure out what kind of astrophysical objects it's like, what kind of astrophysical events it's like actually end up generating. It's like these gravitational waves. And so in that sense, numerical relativity plays a critical role in trying to make that connection and to address that inverse problem. So let me try to frame this. It's like from a mathematical setting. So the Einstein equations, it's like can be derived. It's like using a Lagrangian perspective. It's like using what is known as the Einstein-Hilbert action. And the Einstein-Hilbert action is defined, it's like on Lorentzian metrics in the following way. And if you look at the corresponding Euler-Lagrange equations, you end up with what in the Einstein field equations. And the main take-home message, if you will, it's like for this is that this gives you a second-order gauge field theory. And the space-time diffeomorphisms are the associated gauge symmetry groups. So I'll say a little bit. It's like why that's significant. It's like from the point of view of both the mathematics as well as the numerics. So a gauge symmetry, of course, is a continuous local transformation. It's like under field variables, which leaves the system physically indistinguishable. And local here sort of has to do with the fact that the symmetry transformation is also dependent on where you are in space-time. And it's as opposed to, say, a more globally rigid, it's like symmetry transformation. So a consequence of this is that the corresponding Euler-Lagrange equations are underdetermined in the sense that if you just look at the evolution equations in and of themselves, they're insufficient to propagate all the fields. And there is a decomposition, if you will, it's like of the variables into kinematic fields, which have no physical significance, and dynamic fields and the conjugate momenta, which are the ones which carry the physical information. At the same time, it's like the Euler-Lagrange equations are in some sense overdetermined in the sense that if you look at a problem as an initial value problem, then you don't have arbitrary freedom. It's like to specify the initial data on the Cauchy surface. And so the initial data has to satisfy usually an elliptic constraint. It's like in order for the problem to make sense. And so there's a sense in which all these things can be viewed as degenerate systems. And I'm going to sort of suggest that a generalization of basically symplectic and Poisson geometry, it's like known as multi-Dirac geometry in mechanics, is the natural setting. It's like for studying these kind of problems. OK, so let me sort of just give you a brief example of what I mean by a gauge field theory. So I'm going to look at electromagnetism. If you look at E and B fields, which are electromagnetic fields respectively, you can write down Maxwell's equations, of course, in terms of the scalar and vector potentials in the following form. And one can check that the following gauge transformation, which depends on f, which is a scalar valued function, leaves the equations invariant. And so it's like, so this is an example of a gauge symmetry. And one of the things I said was that if you have a gauge symmetry, then you have constraints, it's like on the initial data. And the corresponding Cauchy initial data constraints are given as follows, where the superscript 0 just indicates the value, it's like on the initial Cauchy slice. So, and then the other aspect had to do with the fact that you don't have enough equations, if you will. It's like to evolve all the fields forward. And in some sense, this is really just due to the fact that you have a symmetry. And there's a sort of parametric family, if you will, of mathematically equivalent solutions. And the physics doesn't tell you which one of these things to pick. Okay, so in order to obtain, it's like a specific solution, then one typically does this through the choice of a gauge condition. For example, you could have the Lorentz gauge or the Coulomb gauge. And the problem, it's like from a numerical perspective, if you will, is that there's almost a chicken and egg problem, right? So if you're trying to solve these things analytically, it's like it almost feels like you have to pick the right gauge, and if you pick the right gauge, then the equations become nice. It's like, and it's easy to solve. But you sort of need to know the solution behavior at some level, it's like in order to choose this gauge. And if you're doing things numerically, there's no a priori assumption that it's like a global choice of gauge might be an appropriate one. And so, so one of the questions, it's like, which I'm interested in studying more is, it's like, is there a way to avoid picking a gauge? It's in a prescribed fashion and let, if you will, the numerics, it's like pick that for you. Okay. So, all right. So one of the consequences of symmetries in a Lagrange and a Hamiltonian system is the connection, if you will, with conservation laws via Noether's theorem. So if you have a continuous symmetry of a Lagrangian action, then there exists a corresponding Noether quantity which is conserved in time. And the simplest example of this comes from classical mechanics, where if you have a time-invariant action, that implies the conservation of the Hamiltonian, which is usually identified with energy. Okay, so time translations, it corresponds to conservation of energy. And then in the case of gauge field theories, what happens then is that there is a Noether current. Okay, the Noether current satisfies the continuity equation, and with an appropriate choice of boundary conditions, when you integrate this Noether current over a space-like surface, then you get a conserved quantity known as a Noether charge. So for electromagnetism, it's like these are the Noether currents, and then the Einstein-Hilbert action, it's like yields, it's like the stress energy tensor, it's like as a Noether charge for your space-time diffeomorphism symmetry. Okay, so let me say now, it's like what the implications are of gauge invariance, it's like in general relativity. Okay, so in addition to Noether's first theorem, it's like which relates sort of symmetries to conservation laws, there's also what is known as Noether's second theorem. So Noether's second theorem more or less says that when you have some sort of gauge symmetry, then what that means is that when you look at the corresponding Lagrange equations, they're not functionally independent of each other. Okay, so if you just pick some subset of those equations, then the rest of them are automatically satisfied once that subset is satisfied. So, so in the case of GR, right, the space-time diffeomorphism symmetry implies that only 6 of the 10 components of the Einstein equations are independent. And oftentimes it's like you see this, it's like in numerical relativity codes that you only need some subset of the equations to propagate the solutions forward. It's like, and then the rest of them are used as a posteriori error estimators. It's like to drive, it's like the adaptive mesh refinement. Okay, so anyway, so the way you typically it's like address this is by using gauge conditions. You might choose it's like the maximal slicing gauge or the Donder harmonic gauge, and the Donder gauge is Lorentz invariant and is oftentimes used it's like for gravitational wave simulations. And when you formulate this, it's like sort of GR as an initial value problem, then the Cauchy data is constrained. It's like, and in particular, you have to solve this Gauss-Kodassi equations. It's like on the initial Cauchy surface. So, so the gauge symmetry, if you will, it's like implies that you have, from the point of view of a variational principle, a degenerate one in the sense that, again, it's like if you just apply Hamilton's principle, it's like to the problem, it's like then you don't have a unique, it's like extremizer of the action. It's like, but again, you have this parametric family, if you will, it's like of solutions which are all related by the gauge symmetry group. So, so those observations, if you will, it's like inform some of our approaches. It's like towards studying a geometric approach to discretizing general relativity. So, so the main point is that general covariance it's like plays, I think, an important role. It's like in relativity. And so what that has led us to do is to avoid a sort of space-time tensor product discretization. It's like of a mesh, which presupposes that you have a global slicing of space-time. And the reason for this is that we don't want to prescribe it's like the topology of the space-time. It's like ahead of time, and it's like rather would like to allow it to evolve, if you will, it's like as part of the simulation. And so instead, we're considering sort of space-time simplicial meshes, right? And the other thing is that we're using this notion of multi-Dirac mechanics, which is based on a Hamilton-Pontryagin variational principle for field theories that is well adapted to degenerate field theories in a way which I'll explain a little bit more. So finally, it's like, it's like one of the reasons, if you will, people use variational integrators and variational discretizations is that they automatically satisfy a discrete version of Noether's theorem. But in order to do that, you need to construct the discretization in such a way that it respects the gauge symmetry. So, so in order to do this, it's like this involves the construction of what we call gauge-equivariant approximation spaces. And these gauge-equivariant space-time-fine elements, if you will, lead to gauge-invariant variational discretizations. And because of discrete version of Noether's theorem, then it satisfies a discrete multi-momentum conservation law. So that's sort of the motivation, if you will. It's like for why it is that we're approaching discretization in this way. It's perhaps orthogonal to the way things are currently done, but we're interested in trying to build numerical methods which automatically exhibit various conservation laws. Yeah. So let me explain to you what Dirac Mechanics is all about. Okay, so normally it's like you have Lagrangian mechanics, which is defined on the tangent bundle to a configuration space, or you have Hamiltonian mechanics, which is defined on the cotangent bundle of a configuration space. So what Dirac Mechanics is sort of a synthesis of those two perspectives. If you are thinking of it from the point of view of optimization, it's a combined primal dual formulation of the problem. And so you have the Pontryagin bundle, which is this sort of fiber product of the tangent and cotangent bundles, and it has local coordinates which are position, velocity, and momentum. And then the Hamilton-Pontryagin principle states the following. It's really sort of Hamilton's principle where you have the action integral involving the Lagrangian, but you relax the assumption that the velocity is the time derivative of the position, but then you reimpose it using a Lagrange multiplier. So the P here, which is the momentum, is also a Lagrange multiplier in this formulation. And you might say, well, why in the world do you do this? And the reason to do this is that when you write down the corresponding Euler-Lagrange equations for this extended formulation of the problem, you get the what is called the implicit Euler-Lagrange equations, which are given here. And in particular, this then becomes a system of first-order equations, which is equivalent to the usual second-order Euler-Lagrange equations when you eliminate the momentum variables. Okay, but the point here is that you've explicitly imposed what is known as the primary constraint, which is that the momentum is the image of the Legendre transform. Usually this doesn't matter. It's like you have a Lagrangian which is non-degenerate because the Legendre transform in that situation is invertible. But when the Legendre transform is non-invertible, it's like then imposing this condition is essential. It's like to getting the equations so that they will propagate forward. Okay, so the fact that you have this explicit, enforcement of the primary constraint, if you will, is one of the motivations for using this Dirac formulation of mechanics for degenerate problems. So let me explain now how you do extend all of this. It's to a PDE setting. So instead of just having time as an independent variable, now it's you have a base space, which is n+1 space-time, and then you have configurations over this. So if you think of the horizontal space, it's as being space-time, then the vertical space are the fields over it, and then you choose a configuration which is basically just a section of this fiber bundle. So more or less that's just a fancy way of saying that for every point in space-time you give a field value, it's to that, all right? And then what you want is to formulate the analog of the tangent bundle, and the analog of the tangent bundle involves taking the first partial derivatives of the fields with respect to the space and time directions, and this gives you what is known as the first jet bundle associated with the configuration bundle. So with that in mind, now you can add some physics to this. It's you can write down Lagrangian density, which is a map from the first jet bundle to an n+1 differential form on space-time. Once you have this object, what you can do is that you can take a section, you can look at its jet extension, evaluate the Lagrangian density on this. This gives you an n+1 differential form, which you can integrate over an n+1 dimensional space-time domain to give you an action, okay? Then, as is the case with the usual Hamilton's principle, you require that this action is stationary with respect to prescribed boundary conditions. So this gives you the equations of motion. So in coordinates, it's like you can write down, it's like the Hamilton-Pontryagin principle for field theories. Here is the Lagrangian density term. It's like in some local coordinate representation. And again, you're making the assumption that the jet variables are in some sense independent, it's like from the field variables, but you reimpose the relationship, it's like via a Lagrange multiplier. And when you write down the Euler-Lagrange equations to this, it's like you get these implicit Euler-Lagrange equations. So one thing which is interesting now is that, as you might expect, it's like in a covariant field theory, the Legendre transform now no longer just encodes, it's like the multi-momentum, but it also includes the energy as well. So it gives you sort of a four-dimensional covariant object, it's like which encodes both the energy and the momentum in it. Okay, so one thing I should mention is that the reason to take this multi-symplectic perspective, if you will, as opposed to perhaps the more common infinite-dimensional Hamiltonian or Lagrangian perspective, is that it's like you have this space-time diffeomorphism symmetry. It's like acting on the problem, and so if you have the usual infinite-dimensional Hamiltonian approach, the way you do this is that you pick a slicing of space-time, okay, and then you sort of integrate. It's like this. Lagrangian and Hamiltonian. It's like over that, it's like, and you can think of it as an infinite-dimensional Lagrangian and Hamiltonian field, infinite-dimensional Lagrangian Hamiltonian system. All right, but the problem then is that the space-time diffeomorphism symmetry acts on this full space-time, and it doesn't preserve the slicing. Okay, so if you prescribe a slicing, it's like then it's like you won't have the full space-time diffeomorphism symmetry acting on this object. And that sort of interferes with our goal of trying to construct methods, it's like which exhibit all these conservation properties associated with the full space-time diffeomorphism symmetry. So that's the reason why we've been taking this sort of space-time point of view as opposed to infinite-dimensional time parameterized point of view. Okay. All right, so given the fundamental role of gauge symmetries and the associated conservation laws in field theories, it's natural to consider discretizations that preserve these properties. And there has been a lot of interest in the numerical analysis community. It's like in a class of methods known as geometric integrators. So these are numerical methods which preserve geometric properties such as symplecticity, momentum maps, Lie group homogeneous space structures in the dynamical system to be simulated. And one of the reasons why this is of significance is that the continuous dynamical system is like evolves on the level sets, it's like of these geometric objects. And so, having numerical methods which respect that conservation property means that you're evolving, if you will, on the same constrained spaces. Okay, so this oftentimes results in numerical simulations with better long-time numerical stability and better qualitative agreement with the exact solution. So let me now briefly talk about how one goes about doing this first for mechanics, and then it's like in the field theoretic setting. Okay, so you start with Hamilton's principle, which states that the action integral, which is the integral of kinetic minus potential energy, is stationary. It's like and then one way to discretize this is to imagine sampling that trajectory of a bunch of points. It's like on the configuration space. And then requiring that some discrete version, if you will, it's like of that action integral is stationary with respect to variations of these internal control points. So the object which comes into mind is what it called the discrete Lagrangian. It's a function of 2 points. It's like on the configuration space, and it's supposed to be an approximation of what we call the exact discrete Lagrangian, which is the action integral over a short time interval. It's just a short time interval action integral evaluated along a solution curve which satisfies the Euler-Lagrange equations in the interior and satisfies the prescribed boundary conditions associated with Q0, Q1. Okay, so it's easy to convince yourself that this is related to Jacobi solution to the Hamilton-Jacobi equation. And once you have that, it's like you can construct a discrete version of Hamilton's principle, which involves summing these discrete Lagrangians. It's like over a sequence. This gives you an approximation of the action integral. And requiring that the variations of that are stationary, okay? And the associated, it's like stationarity conditions are what we call the discrete order Lagrange equations, which are given here. You can see that it involves the solution at the previous time, the current time, at the new time. And so you can think of it as as implicitly defining a map which takes pairs of points. It's like two pairs of points. So given the solution at the previous time and the current time, it'll tell you the solution at the current time and the new time. So it allows you to time march this forward. And that sort of makes sense. It's like because you really have a second order differential equation which you're trying to discretize. If you don't want to think of it, it's like as a method, it's like involving two copies of the configuration space. You can also introduce a momentum variable, and then you'll end up with this form of the equations. And this is, of course, nothing more than a characterization of a symplectic map in terms of type 1 generating functions. And indeed, it's like the discrete Lagrangian is is a type 1 generating function of a symplectic map. You want to construct it in such a way that it approximates as well as possible Jacobi's solution of the Hamilton-Jacobi equation. All right, so these things have been applied. It's like to many applications. It's like in multi-body systems. So these are examples. It's like coming from mechanics. It's like this is a double spherical pendulum. This is articulated rigid body in perfect fluids. And this is tethered spacecraft. It's like for astrodynamical applications. This is some work done by Todd Murphy at Northwestern. It's like on applying these kind of ideas. It's like to biomechanical systems. It's like human prosthetics and stuff like this. And you can extend this, as I said, it's like to continuum systems. It's like primarily to elasticity. It's like in plasticity problems. All right, so why would one do this? It's like, what's the motivation, if you will? It's like, from a mathematical perspective, to do all this stuff. So one of which is that you have a discrete version of Noether's theorem. As I said, if you have a discrete Lagrangian, which is sort of G invariant under the diagonal action, it's like in the following way, then there's an associated discrete momentum map, it's like which is preserved by the discrete flow. Okay, so there's a discrete version of the relationship between symmetries and conservation laws, which is automatically satisfied. It's like, and so the task then is constructing these discrete Lagrangians in such a way that they are group invariant in this way. And then the other thing is like has to do with error analysis. So instead of directly analyzing the numerical method which you get, you can analyze just the extent to which this scalar value function, the discrete Lagrangian, approximates the exact discrete Lagrangian. So this is oftentimes much easier. And in addition to that, we have developed meta theorems which allow you to say that if you construct this discrete Lagrangian in a prescribed way, we can relate the properties of the discrete Lagrangian with properties of the ingredients, if you will, which were used to construct this discrete Lagrangian. So I'll talk a bit more about that. Okay, so other motivations, if you will, it's like for using symplectic methods, particularly in the context, I think it's like of, it's like inverse problems is the connection with adjoint sensitivity analysis. So if you give me a system of differential equations, even if they're non-Hamiltonian, when you take the adjoint of this and you combine it, it's like with your general equations, that system is Hamiltonian. Okay, and it turns out that the condition that that combined system is symplectic is absolutely critical it's critical to describing, if you will, the relationship between the primal and the adjoint variables. Okay, so the implications of that show up. It's like when you try to do, say, optimization. It's like, optimal trajectory generation. And in particular, it's like you can, given a continuous system, you can ask whether if you discretize the system and then take its adjoint, that's equivalent to taking its adjoint and then discretizing. Okay, and it turns out that when you have a symplectic discretization, then those two things commute. Why is that significant? That's significant because when you do, say, optimal trajectory generation, it's like using a two-point boundary value problem perspective, then what usually you want to do, it's like if you want to do this right, is that you need to take the adjoint of the numerical discretization, it's like of the equations of motion. So this is usually an unpleasant thing to do because the numerical method itself is quite complicated. And so what people oftentimes do instead is to take the continuous adjoint and then discretize that with some numerical method. So why is that a problem? That's a problem because when you take the continuous adjoint and then discretize that, you don't necessarily end up getting a descent direction for the discrete problem where you've discretized it. So what ends up happening then is that when you go and try to solve this, it's like shooting problem, the numerical method may not converge. And so that's one example of where having a method which is symplectic, it's like plays an important role. And of course, sensitivity is a big part of of many methods. It's like having to do with inverse problems. And then the other thing is that there's been some recent observations that there's what's known as Nesterov's accelerated optimization methods. It's one of those kind of things with an optimal rate of convergence. It's like given a certain class, article class, it's like it's like information, if you will. It's like about the thing you're trying to optimize. And you can view these things as discretizations of the flow of a time-dependent Bregman Lagrangian. So that's sort of an interesting connection, if you will, between mechanics and optimization. And there's a similar thing, it's like what shows up, it's like between mechanics and information geometry. And information geometry, it's like in turn, it's like has nice connections with machine learning. So all I'm basically saying here is that even if you are working in problems it's like which don't have it's like a Lagrangian Hamiltonian structure, it's like this kind of thing seems to show up it's like in unexpected ways. Okay, anyway, so let me sort of get back to the heart of the matter. So now I want to construct one of these things. It's like and one way to do this is to reformulate the exact discrete Lagrangian in the following way. So I'm going to say I'm going to evaluate the action on some curve, but I'm going to extremise this object over the class of twice differentiable curves which satisfy the boundary conditions. Okay, and this is clearly equivalent because the stationary conditions for this extremal problem is nothing more than the Euler-Lagrange equations, and so that's equivalent to the Euler-Lagrange boundary value problem formulation of the discrete Lagrangian. So what you do next is to get a computable object is to replace this infinite dimensional function space, it's like of twice differentiable curves, with some finite dimensional function space, and to replace the integral with a numerical quadrature formula. And let me just sort of say at the onset that if your function spaces are group equivariant, then they will give you a group invariant discrete Lagrangian. So what I mean by group equivariant function spaces, imagine you have some sort of procedure where given a bunch of points, it's like I give you a curve which is parametrized by it, right? It doesn't have to go through the points, but it's parametrized by those points. If I take a bunch of points and then I transform them by some symmetry action, and I get a new curve which goes through this, then I want that the old curve and the new curve related, it's like by the same root transformation. And if that's true, then we say that this prescription, it's like for constructing this finite dimensional space is group equivariant. Okay, so that's the thing which I want. All right. So the other thing is that because the way we've constructed or are proposing to construct this computable discrete Lagrangian involves the choice of a finite dimensional function space, one very natural question to ask is whether or not it's like the numerical method you end up getting it has an optimal rate of convergence. So what does one mean by that? So if you have the exact solution and you measure the distance between the exact solution and some numerical solution in some appropriate norm, right, then you would like that this error is bounded from above by some multiple of what is known as the best approximation error. So QD was chosen from this finite dimensional function space. So it's natural to ask, well, if I chose, it's like if I have a solution and I allow myself to vary over every element in that finite dimensional function space and look at the error you get, right? What's the smallest error you could get, right? And in some sense, this is the best you could hope for. Okay, so this is what's known as the best approximation error. And if your numerical method is bounded by, the numerical error is bounded by some multiple of this best approximation error, then what that allows you to do is that it allows you to convert the problem of constructing good numerical methods to the problem of constructing good approximation spaces. Okay, so that's the reason why you might care. All right, so it turns out that you can do this. It's a little bit technical because the discrete Lagrangians we constructed were extremizers of some variational problem. And so in order to prove that you have this convergence, you're doing something like gamma convergence. Okay? And in fact, you're doing something stronger than that because this is the extremal and not the minimum or the maximum. And we don't just care about gamma convergence, we care about the rate of gamma convergence, and we want it to be related to the best approximation error. Okay, so it doesn't really matter. It's like all that's necessary to show is that you can do this. And there's some sort of fairly standard regularity assumptions. The one which is a little bit non-standard is the assumption that the discrete and continuous trajectories minimize as opposed to just extremizing their actions. So that requires a little bit of work, okay? And but for Lagrangians of this form, it's like of this sort of quadratic minus potential form, and for sufficiently small h, then this assumption can be shown to hold. And then the methods which you construct from these are order optimal. And if you were to do what are known as spectral discretizations, where you fix the mesh size, but you let the polynomial order go increase, then the associated methods are geometrically convergent, okay? Okay, so you can show it's like that as you change the class of polynomials you use, it's like it has the rate of convergence you expect it to have. What's a little bit more interesting is this geometric convergence plot. It's like where you fix the mesh here, it's like, and you let the polynomial order increase. You take more and more Chebyshev, it's like polynomials. And notice there are two lines here. You might ask, it's like, why do we have two lines? It's like, and what's the circle and what's the dot? Okay, so the so the error analysis is like, as it's traditionally formulated, just tells you what error you make. It's like at the nodes of the mesh, okay? But because of the fact that you've constructed this solution, it's like using some distinguished choice of function. It's like in a finite dimensional function space, right? The problem is variational. You've picked, if you will, this distinguished element of the finite dimensional function space in order to construct a numerical solution. It's natural to ask whether that distinguished element is itself a good approximation of the solution in the interior of the mesh, okay? And it turns out that it is, okay? And you can prove that that interior solution converges, but at half the rate, it's like of the solution at the nodal points, okay? So that's what these two lines represent. This is the convergence of the nodal values, and this is going to give you the convergence of the interior solution. Okay, so it still converges, just at a slower rate. Okay, so what are the implications of this? The implications of this are that when you apply this method to problems, it's like you can take ridiculously large time steps. Okay, so this is just a simple, it's like ODE problem. It's like where you've done sort of a n-body approximation of the inner solar system. The thing on the left is the JPL ephemeris calculation, and the one on the right is the mathematical abstraction, if you will, of the problem. But the notable point is that I've taken a time step of 100 days, and Mercury is resolved in the calculation, and Mercury has an orbital period of about 81 days. So I've taken a time step which is larger than the fastest orbital period in the problem, and nevertheless I don't get absolute garbage. And it's really because, if you will, of this property that the interior solution is actually well approximated as you allow the polynomial order to increase. The same thing is true for the outer solar system, right? So now the time step is 5 years, and this is again larger than the effective, it's like fastest orbital period in this problem. So you can also extend this, it's like to rigid body simulations, it's like which evolve on Lie groups, okay, and this is just meant to illustrate that if you were to use explicit Euler or even a very highly resolved adaptive method, it's very, very difficult to respect. It's like both the energy conservation and the angular momentum conservation. Whereas if you used even a low order Lie group variational integrator, you get perfect sort of agreement. It's like in terms of those conservation laws. Okay, so all that is sort of just a baby problem. It's like for ODE problems, how do you extend all these ideas to the PDE setting? So there is the characterization of symplectic maps in terms of generating functions. This is something which you'll see, it's like in any classical mechanics class. And the reason why these things are interesting or important, it's like, is because when you take then the second exterior derivative, it's like of the generating function, then this calculation together with the form of the symplectic map sort of automatically shows that the map actually is symplectic. Okay, so how do you generalize that? So you want a PDE analog, if you will, of Jacobi solution, and it's sort of the obvious thing if you think about it, right? So what's happening here is that you're specifying the function values or the solution values at the boundary of the time interval, it's like which you're looking for, and then you evaluate it, it's like on the action I mean, you evaluate the action, it's like on a curve which satisfies the Euler-Lagrange boundary value problem. So we want to do something similar. If you have a PDE exact discrete Lagrangian, what you want to specify is the field values on the boundary of a space-time domain. That's the data on the left-hand side. And I want to evaluate the action then on some section which satisfies the boundary conditions and satisfies the Euler-Lagrange equations. All right, so this is what we call the boundary Lagrangian or the exact discrete Lagrangian in the PDE setting. So that's one thing. And then the second question is, well, what's the PDE analog of this condition? Okay, so if you look at this, this more or less is saying that I take this discrete Lagrangian and I allow myself to vary the the data, if you will, okay, on the boundary. Okay, so you do this, you vary the data on the boundary, and then this is somehow related to the momentum. Okay, so that can't possibly be exactly true in the PDE setting because now it's like you have both space and time directions. Yeah, and so what that means then is that you have to have a component of the momentum. Okay, so it turns out that it's essentially the normal component of the multi-momentum, but this is the equation you end up getting. Okay, so again, the take-home message is that once you take these kind of things into mind, then you can construct a discrete boundary Lagrangian, and you want it to be, if it's invariant with respect to a lifted action of gauge symmetry group on the boundary data, then it will satisfy discrete multi-momentum conservation law. And in order to construct one of these things, it's like you have to have these group equivariant approximation spaces. And again, the implication is that you want to construct something which is group equivariant. But again, what complicates matters is that in GR, it's like the finite element has to take values in the space of Lorentzian metrics, which is not a convex space. Okay, so you have to be a little bit careful. All right. So you have the Lorentzian metric tensors. It's like they are 4x4 symmetric matrices. It's like non-zero determinant with this signature. And you want to construct a interpolation problem the following way, right? So if you have same metric values, it's like at the nodes of a space-time simplex, you want the interpolant, which is a map from the space-time simplex, it's like to the space of Lorentzian metrics, it's like to recover the data at the nodes, okay? And that every interpolant value actually is in the space of Lorentzian metrics, and it has this sort of orthogonality. Well, it has this sort of group equivariance property that if you have something which is in the indefinite orthogonal group and you conjugate, it's like the data by that, then the interpolant transforms in the same way as well. So this is the group equivariance property which I was talking about. So why is this non-trivial? So naively, if you take these two Lorentzian metrics and you did the midpoint of that, then you end up with this sort of metric which is not Lorentzian. Okay, so this is just telling you that sort of naive component-wise interpolation doesn't give you what you need, so you have to be a little bit more careful. So what we're going to do then is we're going to try to do something which is similar to what we have. It's like in in the Lie group setting, it's like which is that we use, it's like, so in the Lie group setting, it's like you oftentimes construct, it's like objects, it's like with the right equivariance properties by using the exponential map, which relates the nonlinear object which you care about, it's like with some underlying linear space, okay? So the problem, of course, is that the space of Lorentzian metrics is not a Lie group, but it has structure, it is a symmetric space, and because it's a symmetric space, you can do sort of a similar construction that in particular you can identify the symmetric space in a locally diffeomorphic way, it's like with a linear space, and then do the construction this way. So, all right, so this Lorentzian metric is diffeomorphic. It's like to this general linear group quotiented by the indefinite orthogonal group, all right, in the following way. And so it's a quotient space. It's like, and the point is that every coset, it's like in this quotient, has a canonical representative using a generalization of the polar decomposition in the following way. And in particular, it's like this canonical representative Y. If you take the matrix log of that, this lives in a linear space which is called a Lie triple system, which is given by this floating property. Okay, so its Lie triple system is not a Lie algebra, but nevertheless, it's like you can identify this Lie triple system. It's like with the J symmetric matrices. It's like which in turn it's like is associated with this equivalence class of matrices that's like in this quotient space, and then that's related to a specific sort of Lorentzian metric. So you just have to check that basically all these maps, it's like sort of, it's like local diffeomorphisms, and when you do that, then you have a local diffeomorphism between the sort of this Lie triple system, it's like, and the Lorentzian metrics. And then, it's like you take all the data, it's like in the Lorentzian metrics, you pull it back to the Lie triple system, you do the interpolation there, and then you sort of move back to it, right? So that's basically what's happening. And when you do that, it's like you end up with an interpolation formula which looks like this. Okay, and it has nice properties. It's signature preserving. So in particular, if you give it Lorentzian metric value data, it's like it will stay Lorentzian metric valued. It has this frame invariance or group equivariance property. And all right, so we haven't. It's like combine all these pieces together. It's like to construct a discretization or GR. It's like, but just as sort of proof of concept, it's like we've applied the interpolant. It's like to interpolate, it's like the Schwarzschild metric. It's like, and you can show that it has the right rates of convergence. It's like if you have underlying linear shape functions, and if you sort of push up to quadratic shape functions, it has the higher rate of convergence which you expect it to have. Okay, in both L2 and H1. So, so I'm going to skip. It's like this part here, and let me just sort of briefly say that you can extend all these ideas as like to more general symmetric spaces. It's like, and it has applications to a bunch of other interpolation problems. So, all right. So, so let me summarize by saying that gauge field theories exhibit gauge symmetries that impose Cauchy initial value constraints and are also undetermined. And these result in degenerate field theories that can be described using multi-Dirac mechanics and multi-Dirac structures. I've described for you a systematic framework for constructing and analyzing variational integrators and how to extend this, it's like, to the case of Hamiltonian PDEs. And in particular, it's like if you want to get numerical methods which are multi-momentum preserving, these can be constructed, it's like in the variational integrator framework, it's like by choosing group equivariant finite element spaces. And finally, it's like I showed briefly how you can construct Lorentzian metric valued group equivariant finite element spaces using a generalized polar decomposition, and you can actually implement this very efficiently. So it's not just that you can formally do it, but you can actually do this efficiently. So these are some references, and I'll stop here. Thank you.